Howdy, I'm Matthew Kutzmode, and I will be introducing you to secondary authentication using recurrent neural networks, research I did last year with Matthew Berry for 704 Data Analytics for Cybersecurity. Everyone is familiar with secondary authentication like texted or emailed verification codes, hardware security tokens, time-based one-time passwords, duo push, or more security questions, but all these methods rely on an additional step, which can be just another point of failure. So what if the very act of entering a password provided the secondary authentication? Welcome to the highly researched field of keystroke dynamics, where precise keyboard timing data is captured while a user is typing. Everyone has their own unique typing pattern, almost like a fingerprint. So can we train AI to know that you are the person at the keyboard typing the password? This may be possible by studying exact timings, like how long you press or release keys, as well as the intervals between presses or releases. Now we need AI because we need to recognize the user's password typing and its variance over time. But what AI tool to choose? We're going to dig into the inner levels of AI, machine learning, deep learning, neural networks, and at last we come to what we chose for our research, a recurrent neural network. A recurrent neural network is defined as a type of artificial neural network which uses sequential or time series data. And how it works is like this. We feed the RNN a user's password typing, which runs it through a hidden layer that constructs weights and biases. It then recurses, how it gets its name, to use the next password typing and adjusts the weights and biases again. At the end, it outputs whether or not the user is authenticated, i.e. if their password timings match what is normal for that user. A couple of points about our research. We wanted to study a fixed password, use an RNN, which is not commonly used, test using n-grams, and lastly, compare accuracies of variances from other users. So in summary, only looking at a fixed short repeated password can we train an RNN to detect users from imposters. To answer this, we first found our data set of over 20,000 password timings where everyone entered the same short password, .ty5ronald, don't ask me what it means. We wanted to investigate what the timings looked like, so since no other research gave any pictures, so we created animations for each. These are a sample of the keystrokes with 3 specific users chosen: the most variant user, 36, the least variant, 31, and the middle variant, 46. If you're interested in our implementation, we use the Keras library provided by TensorFlow to train a simple RNN model, and the other details describe how we opted for a higher number of hidden layer nodes and a decreased learning rate. For data prep, we chose the user's 400 entries as the good data, and then for bad, we chose 400 random entries from the other users. We then split that into our training, testing, and validating sets. We also wanted to compare our normal linear data with sliding window 3 grams, which, as it suggests, we iteratively read 3 keystrokes at a time instead of reading the whole password timing at once. In order to understand our results, we have to talk about rates. In the original K&M report, they used equal error rate and zero miss rate to rank performance. As depicted, equal error rate is the middle point between the false and positive and false negative rates, and the zero miss rate is the false alarm rate that is tolerated in order to catch 100% of attacks. So we ran our model and achieved this ROC curve. Looking at it, you can pick out our 3 users: 36 to the best, 46 slightly behind, and 31, the least variant, trailing behind. Overall, our RNN achieved an EER of 0.091 and ZMR of 0.298, which compared to the original datasets, authors' results, it outperformed all their algorithms. And then as well as the most similar KNS paper, it also outperforms their algorithms. To give you a sense, the EER means that we stop 91% of illegitimate access while allowing 91% of legitimate access, and the ZMR, on the other hand, stops 100% of illegitimate access while allowing 70% of legitimate access. Our results may sound good, but there are limitations, like this was not a real-world scenario since the users entered the same password, and then the bad data could have been misrepresented. And then, of course, password managers would totally block collecting keystroke dynamics, and then other factors could be in play, like changing keyboards, typing a different language, etc. This research can be improved in the future with attempting to generate negative data or find methods that do not require negative data, and as well as getting closer to continuous training by feeding parts of data at a time. We could also find the minimum number of password timings to get good accuracy. Besides RNN, there have been greater successes with other neural networks in this exact application and dataset. For instance, Chaker et al. Saw 97.7 accuracy with an augmented CNN, and Baynath et al. Saw the same accuracy with a multi-layer perception neural network, and the same author also found an accuracy up to 98% by using a chaotic neural network. This leads me to the conclusion that although there are hurdles to overcome, I believe a neural network could very well provide a secondary authentication in the near future. Here's a list of references for this project, both sites for gathering details as well as research papers in the field. Thank you for watching, and I hope you learned something about using an RNN for secondary authentication in the vast study of keystroke dynamics. Thank you.